Hello everyone. We're going to solve this redox problem. So I'm going to read out the problem before we start solving the question. The problem says calculate the net potential and standard free energy change for the reaction below. Is this reaction spontaneous? Identify the oxidizing and reducing agents. The equation given here is ethanol plus NAD plus, giving you acetaldehyde plus NADH plus H plus. Okay. So this is the equation given. I'm going to go through the steps of how we're going to solve this particular problem. So in the solution, in the first step, what we're supposed to do is to identify the key reactants and products in this reaction. The key reactants and products being, so on the left side, you have ethanol, and then you have NAD plus, and then you have acetaldehyde and NADH. Typically, when you solve redox problems, it is important to realize that the things on the left side are somehow related in pairs to things on the right side. For example, if you look over here, we have NAD plus, and then on this side we have NADH. So that tells you that there is, if NADH were to be formed, it needed to have come from H plus, NAD plus, right? So you need to kind of mentally form those kind of relationships as you're solving this problem. So this also tells us that most likely ethanol is going to be the source for making acetaldehyde. So something is happening here, but this is how this conversion is going to work out. Okay, so we make a mental note of this, and then we move on to step number 2. So since we are doing problems on redox reactions, it is important that you always keep a table of standard reduction potentials ready with you. If you watched my previous 3 videos on the basics of redox reactions, you will realize that in those problems we have used tables of standard reduction potentials. But one key thing to note here is that the compounds that we are using in this equation, especially compounds like NAD plus and NADH, those are all biochemical compounds. Those are not simple chemical compounds. You won't find them in a regular standard reduction potential table. So when you see these compounds such as NAD plus, NADH, those compounds are coming from biochemical reactions. So there is a separate table, separate standard reduction potential table for biochemical reactions. So it's important that you pull that up and keep that in front of you as you are working out this problem. And these tables can be very easily found by using a Google search. Like if you type in standard reduction potentials for biochemical reactions, then it'll give you a table. If you simply type standard reduction potentials, then you will find that as well. But you're gonna find that those may not contain all these biochemical reactions in them. Okay, so it's something to keep in mind as you are working out this problem. So this particular example is a biochemical reaction. So we want to use a table, a standard reduction potential table that is important for that is pertinent to biochemical reactions. Okay, so that's something to keep in mind. So it says here in step 2, match the key reactants and products from step 1 to 2 half reactions in the table of standard reduction potentials. That means we're going to go to the standard reduction potential table. In the table, you're going to see a whole bunch of reduction reactions. You're going to identify 2 reactions in the table that contains the same exact components that you find in this overall reaction. For example, you may find in the table 1 reaction that's pertinent to converting NAD plus to NADH or NADH to NAD plus in the table. So identify that reaction, put a mark on it, and then you're going to need that. And then you may find another reaction that relates ethanol to acetaldehyde and identify that reaction, and then make a note of it, and then keep it there. Okay, so at least you know where to look them up and where they are in that table. Okay, once you find those 2 reactions, just pick out those 2 reactions from the table and then write them down. So if I looked it up in the table, and when I looked it up in the table, I found that I had this acetaldehyde reaction which says acetaldehyde plus 2H plus 2 electrons going to ethanol, and I also wrote down the standard reduction potential for the reaction. And also please pay attention here. Here I'm saying this as E naught prime. If you watch my previous videos, you will see that whenever you see this E naught prime, the prime symbol tells you that these are for biochemical reactions. And I mentioned this in step 1 and step 2 that we are dealing with biochemical reactions. So that means you have to use the table of standard reduction potentials that deals with biochemical reactions. And then the same way, I went ahead and then wrote down the the reaction for the NAD plus going to NADH, and then this is the reaction that we have here. So I've marked them as reaction 1 and reaction 2 because we're going to manipulate them in the future. So at that point, it's helpful to identify which is reaction 1, which is reaction 2. Okay, so we've gotten the 2 reactions. Now we are going to move on to the next step. So what do? So what is our goal? Our goal is to take these 2 half reactions from the table and then manipulate them in such a way that in order to obtain this final equation. Okay, so that's what we're trying to do. So we're going to manipulate these 2 equations that are given, reaction 1 and reaction 2, in such a way that we can obtain this overall reaction given in our problem, because that's what is going to help us figure out all the information that we're asked to figure out. So remember that as you're going through this problem, we are asked to find out a whole bunch of things. We are asked to figure out the net potential. That's item number 1. We're asked to figure out the standard free energy change. That's item number 2. And net potential, when you hear the word net potential, what should come to mind is this symbol, delta E naught. And because we are dealing with biological reactions, this is what we are trying to figure out, delta E naught prime. And then it's a standard free energy change. So if it's standard free energy change, we're trying to determine delta G naught prime. So that's something that we're trying to figure out. And then we're also trying to figure out whether the reaction is spontaneous. And we're also trying to get to the fact that identifying which is the oxidizing agent, which is the reducing agent in this particular overall reaction. Okay, so that's what we're trying to do. So far, so good. We have written down the 2 half reactions and we're all set, and we're going to move on to the next step. So we're going to start from the same step 3, which is where we have written out the 2 reactions. Now in step 4 says that between the 2 reactions, decide which reaction you're going to keep it as it is given, and then which one you're going to flip, because because typically when you solve these problems, we're going to end up keeping one reaction as it is, and then one reaction we're going to flip it, because that's how the equation is going to work out. So if you look here, the first reaction that's given here has the first half reaction has acetaldehyde on the left side. When you compare it to the overall reaction, in this overall reaction, we see that the acetaldehyde is on the right side of the arrow. So that tells that the acetaldehyde here is on the left side, here is on the right side. And the same way, if you look on the other side, we have ethanol on the right side in the half reaction, whereas the ethanol is on the left side of this overall reaction. So if you want to match the reaction number 1 to the overall reaction, we have to flip reaction number 1. But if you look at reaction number 2, we can see that we have NAD plus, which is on the left side. And in this equation, we have NAD plus on the left side. And then we have NADH on the right side. And then we see that NADH is on the right side. That tells us that the reaction number 2 doesn't have to be flipped, but it's just that the reaction number 1 that has to be flipped. Okay, so we know I've made a note here saying, okay, flip reaction number 1, but keep reaction number 2. So I made a note of that because it's going to help me actually do the flip in the next step. So in the next step, step 5, what we're going to do is write the flipped reaction and change the sign of delta E naught. So I'm going to rewrite the equation here. So if you see here, this is our reaction number 1. We have flipped it in step 5. When we flipped it, we can see that the ethanol, which was on the right side, has now gone to the left side over here. The acetaldehyde, which was on the left side, is now on the right side of the arrow. We have written that. And the most important thing here is that this E naught prime value, if you look here, instead of having a negative sign over here for the normal reaction, for the flipped reaction, the sign has changed, because the reactions that we wrote down are all reduction reactions from the table, because the table itself says it's the table of standard reduction potentials. Now we are flipping the equation. When you flip the equation, the whole reaction becomes an oxidation reaction. And when you flip the equation, we have to change the sign as well. We have to flip the sign. Instead of being a negative, we have to change it to a positive. So once you write down this, then you're set to execute the next steps. So now you have written down the flipped reaction. What we're going to do is that after you write down the flipped reaction, we're just going to add the 2 reactions up and then write down the final equation. So on the left side, so let's just focus on the equations over here, these 2 equations. We are just adding everything. Everything on the left side of the arrow falls on one side, and everything on the right side of the arrow falls on the other side. So for example, ethanol is on the left side of the arrow for equation number 1. NAD plus is on the left side of the arrow of equation number 2. 2H plus is on the left side of the equation number 2. 2 electrons are on the left side of equation number 2. On the right side, we have acetaldehyde on the right side, 2H plus on the right side, 2 electrons on the right side, NADH on the right side, and H plus on the right side. So these are the items. So we're going to collect them all and write them together. But before we do that, we cancel out things that you see both on the right side and the left side, and they're exactly the same items. For example, if you look on the left side of equation number 2, we have 2H plus. I can cross it out because there is a 2H plus in this equation on this side, because when we are going to add it, it's going to show up on both sides. So I don't want to repeat writing it. So I'm just canceling that out. And then we also see that there are 2 electrons over here. I can cross that out with the 2 electrons over here. So I cross it out. So that means that we don't have to worry about any of those things. So we just write down the remaining things. For example, we have NAD plus ethanol over here. So that ethanol, sorry. So the ethanol over here. So we can see that the ethanol is, okay, we have the ethanol right over here. And you can see that this ethanol matches the ethanol on the left side. NAD plus is over here. The NAD plus matches the NAD plus over here. And there's nothing else on the left side of the arrow. So we move on to the right side of the arrow. So we have acetaldehyde on the right side. We have acetaldehyde on the right side. NADH on the right side. NADH on the right side. And then we have this H plus over here. And then the H plus over here. Okay. So we write down the overall reaction. And then we just add up these two values, these E naught prime values for the two half reactions. And then we get what this delta E naught. The delta E naught is basically the net potential of the reaction. So we're going to call this delta E naught prime as the net potential. And if you remember, when we were reading out the problem, the first thing that we were asked to solve for, if you look at the very top here, it says get the net potential. So what we have done by going through steps 1 through 6 is that we have, first of all, manipulated the two half reactions to obtain the overall reaction that was given in the problem. Remember, this is the overall reaction that's given in the problem. And by doing that, by going through this exercise, we have taken the standard reduction potential values, and then we flipped this one. The top one was flipped, the bottom one was kept as it is. Once we did that, one reaction became reduction. So this was always reduction because we didn't change anything. We took the reaction from the standard reduction potential table where all reactions are reduction reactions, but we flipped the top reaction. So the top reaction is actually an oxidation reaction. And we know that whenever there is a redox reaction, one part of that, one set of compounds are going to undergo reduction. The other set of compounds are going to undergo oxidation. We've confirmed that. And then we've also obtained what is called the net potential of the reaction. Okay, so we've gotten the net potential. So our next goal is taking that net potential and trying to obtain what is the standard free energy change. As I mentioned, standard free energy change refers to the thermodynamic symbol delta G, but because it's a standard free energy change, it's going to have a knot at the top. It's going to have a knot at the top. And because we're dealing with biological reaction, we're also going to have a prime sign that tells us that delta G naught prime is what we're trying to figure out in the next step. Okay, so how do we do that? So we have the net reduction potential. So if you want to figure out the standard free energy change for the reaction, if you watched my previous videos on the basics of the redox reactions, you'll realize that if you want to figure out the delta G naught from delta E naught, the best equation to use is delta G naught prime, which is the standard free energy change for biological reactions, is going to be given as negative N times F times delta E naught prime. Okay, and in this gray box here, it tells you what each of the terms mean. N refers to the number of electrons that are involved in the overall reaction. Then F refers to the Faraday's constant, which is given over here, 96,485. And this delta E naught value is what we calculated in step number 6, and that number is negative 0.123 volts. So we take these numbers, we're going to plug it into that formula and get the delta G naught prime value. And one important thing to note here is that this value of N, how do we figure out the value of N? If you want to figure out the value of N, you look at the two equations that we wrote down to balance or add up the two reactions. If you remember, the first reaction is an oxidation reaction where ethanol becomes acetaldehyde and it gives up 2 electrons, it releases 2 electrons, and those 2 electrons are being taken up in the step 2 by the NAD plus, and then it becomes NADH. So that means overall in this reaction, ethanol is giving us 2 electrons, NAD plus is accepting those 2 electrons. So that means that overall number of electrons that is involved in this redox reaction is going to be 2. So it's going to be negative 2 times, then you plug in all the constants, and then you're going to solve the next step. So I'm going to show that to you in the next step. So we have everything written out just like what we had before. So now we're going to set up our delta G naught calculation. Delta G naught calculation has -2 times 96,485, which is the value of F, and then the delta E naught value, which is -0.123. And then if you do this calculation, you'll see that the delta G naught, because we have a negative sign here and a negative sign here, negative times a negative is a positive, so you end up with delta G naught value of 223,735.3 joules per mole, which is 23.7 kilojoules per mole. Okay, so this is the delta G naught value that we have obtained for this reaction. So now, next question is asking us, we figured out the delta G naught value. Our goal is to figure out whether is this reaction spontaneous. So we're at this step, we're trying to figure out whether is this reaction spontaneous or not. So how do we decide whether our reaction is spontaneous or not? There are two rules. The first rule says if your delta G naught value is a positive value, then we have to conclude that the reaction is non-spontaneous. That means it doesn't very easily, without any external intervention, it doesn't get from your reactants to product. And then rule number 2 says if delta G naught is less than 0, which is, it should not say a positive value here, it should say a negative value. So this should say negative, sorry. This should say negative. If this is a negative value, then the reaction is going to be spontaneous. If your delta G naught value is less than 0, then it's going to be spontaneous. So in our case, we know that our delta G naught value is this value, which is a positive value. Because our delta G naught is a positive value, we have to conclude that our reaction is non-spontaneous. So this tells us that our overall reaction is non-spontaneous. Okay, so we've answered the net potential part, standard free energy part. We've also answered whether the reaction is spontaneous or not. And then now the last thing that is left to answer is my reaction oxidizing? What is my oxidizing agent? What's my reducing agent? That's what we're trying to answer here. Okay, so how do we do that? So we again go back to our the steps that we use to balance our reaction. So in this reaction, we said that, the first reaction that we wrote down, the ethanol reaction, we flipped it. And then the second reaction that we wrote down, we kept it as it is. And as we were going through this discussion, I said that the reaction that we flipped becomes the oxidizing reaction, because from the table that we, table of standard reduction potentials, when we write the reactions down, both reactions are going to be reducing. But once you flip one of the reaction that you flip becomes the oxidizing reaction. So that means oxidation is happening in the ethanol going to acetaldehyde plus 2H plus 2 electrons. So that's the oxidizing reaction. So that is the oxidizing reaction. The other one is going to be the reducing reaction. The second reaction is going to be our reducing reaction. Okay, so we have that. Now, so the conclusion is the top reaction is the oxidation reaction. Now, how do we, so in the oxidizing reaction, which is the compound that is undergoing oxidation? So if you carefully look at this reaction, here in the top reaction, ethanol is changing into acetaldehyde, and in that process it is releasing 2H plus and 2 electrons. So that is telling you that ethanol is a compound that is losing electrons. So therefore ethanol is the compound that is specifically undergoing oxidation. Ethanol is undergoing oxidation. By the same token, if you look at the bottom reaction, NAD plus, you have NAD plus, it's reacting with 2H plus 2 electrons. That means NAD plus is the compound that is accepting the 2 electrons. Therefore, we know that by definition, any compound that is accepting 2 electrons is undergoing reduction. In this case, we are accepting 2 electrons. So we can say that NAD plus is undergoing reduction. Okay. And if you watch my basics videos, in the basics videos, I go over the fact that the compound that is undergoing oxidation is going to be the compound that is going to serve as the reducing agent. So ethanol, which is undergoing oxidation, is the one that is going to become the reducing agent. And then NAD plus, which is undergoing the reduction, is going to be the compound that is going to be serving as the oxidizing agent, because NAD plus, when it's undergoing reduction, is accepting electrons. So it's actually pushing ethanol to give more and more electrons. So it is forcing the ethanol to undergo oxidation. It's creating the driving force for ethanol to undergo oxidation. Same way, if you ethanol, because it's undergoing oxidation, it's giving a lot of electrons. It's also providing the driving force for NAD plus to accept the electrons. So therefore, because it's actually helping the opposite reaction, so that's the reason why we say ethanol, even though it undergoes oxidation, if you remember, when something undergoes oxidation, it loses electrons. When it keep giving electron, it's actually helpful for the reduction reaction, because the reduction reaction needs electrons. So therefore, the compound that is undergoing oxidation is the one that is the reducing agent. The compound that's undergoing reduction is the one that is the oxidizing agent. Okay, so let's just summarize what we've learned in this problem so far. In this problem, first thing that we did was we started with this equation. This is the overall reaction. For that reaction, we figured out what is the net potential, which we figured out to be delta E naught prime, the value to be negative 0.123 volts. From the delta E naught value, we figured out the delta G naught value, which is a positive delta G naught value. So that tells us that our reaction is actually non-spontaneous. And then we did a little bit of analysis of the overall reaction. And then we identified that ethanol is our oxidizing agent, NAD plus is our, ethanol is our reducing agent, and NAD plus is our oxidizing agent.